right, so we're going to do a small little mini unit on what I like to call categorical or qualitative data. And they really both mean the same thing. And I kind of use those two terms interchangeably. But qualitative and categorical really describe the same kinds of data. We're not going to have a test on this unit. It'll be a quiz that you will have, and it will only cover Chapter 3. It's a nice little short unit. Honestly, we're going to spend 2 days on it, take a quiz, and move on to our next relatively large unit called bivariate data. Okay? So, what is qualitative or categorical data? Let's compare it to something we already know. Univariate was quantitative data. It was measurable. Okay? We measured the lengths of fish, or we measured things. Okay? And that was quantitative, measurable. Categorical or qualitative data is not measurable, but what is it? Devin? Okay, so color, right? Eye color was one of the questions, right? Okay, or one of your homework that you had to talk about. And that is going to be categories. You either have blue eyes, hazel eyes, brown eyes, green eyes, whatever, right? And those are categories that you can count and put people in. Tanner, you want to add to that? What do you mean by that? Okay, and we're going to get to that, and that's very true. And you have to be kind of skeptical about what you're looking at. Kind of like the pie charts I showed you, or wasn't a pie chart, what did I show you last class? With the Scotland vote, right? Remember I showed you they were both, you know, it was voting is a count, or it's a categorical data. You either vote to secede or you don't, or you either approve or you don't, right? So those are called qualitative data also. The big thing here that we're going to talk about, and to really kind of guarantee that it's qualitative data, is you want to be looking for what we like to call counts. Okay? How many people have brown eyes? How many people thought that Scotland should become its own thing? Okay? So we're really looking for counts. Frequencies. Okay? Now, it's not measurable, meaning that we're not going to be creating a histogram, okay? But we are going to be looking at the data in such a way that it goes into these categories of data, okay? Now, there's also pie charts in here. These are the different, what we call data displays to describe categorical data. Pie charts is one. We'll look at a pie chart today. I'm not sure how relevant it is to our lives, but we'll look at one. And only because we don't do them much in AP stats, but I think you see pie charts so much in like the newspapers and news, and it's kind of a nice visual display. So we will look at them. Bar charts, which are very different from histograms, so we'll need to describe the difference between them. Frequency tables, you can go ahead and go if you want. Frequency tables we've already talked about a little bit. Remember how we used our calculator to describe frequency tables? And we're going to look at that with contingency tables. And sometimes these are called two-way tables. Do you guys remember from your reading which way the book called it? Two-way tables or contingency tables? They use contingency? Okay. Another way is two-way tables. Okay. And we'll look at what that means. Contingency. Thank you. And it's all right. I have typos. Yeah, you get a Smartie. Yes. They're right in the back. Andrea, in that bag, there's a bag of Smarties. She found a typo. She found a typo. All right. She was my student last year, so she knows the rule. You got to tell me if you find a mistake of mine, you're a Smartie, and you catch me being a dum-dum. So either one. All right, here we go. So, quantitative versus qualitative. It's going to be important that you understand the difference between these two things. And I've already, you don't have to write all that down. Please don't write it down. Print the notes later if it's anything. But I just want to make sure that you know the difference between them. What does quantitative do? Amounts, well, not amounts. I don't like the words, because amount can be like a count. So maybe not amount might be the word I'm looking for. Quantitative? Well, that's qualitative. Quantitative is something that's measurable, right? Age, income, years of education. These are the examples I'm giving you, okay? But quantitative is measurable. Now, qualitative is what I think you guys were giving me. Did I spell that right, you guys? But the number of things that, if the number of is a count, which would be a qualitative thing. So,
I think that's what he thought he was saying.
qualitative. Yeah, that's what it's. I have to enunciate better. Qualitative versus quantitative.
You gotta drop the E on the measurable.
Are you kidding me? I told him that.
I knew that.
I don't think I spelled it right.
Yeah, it's. Yeah, not that. I knew that. I was
told you
right.
that.
I think they're gonna fight. I think y'all need to chillax. I think we're just gonna have to move on. All right. Qualitative data are things like categorical data, the color of your eyes. Here's one that's hard to put into to figure out which one it is. But these are categories. Okay. So here's a question for you. If I had a set of data and I wanted to gather information about 9th graders, 10th graders, 11th graders, and 12th graders. Is it okay? Oh, I thought you had like a cramp in your leg or something. 9th, 10th, 11th, and 12th graders. Which kind of data would that go into? Measurable data or categorical data? Okay. So sometimes that bothers people because 9, 10, 11, and 12 are numbers, and so they think that should be like numerical or measurable data, but it's not. They're really categories: freshman, sophomore, junior, senior, right? So just keep that in mind because we tend to use those as examples quite a bit in this class. So yes, if we're talking about breaking them up into classes like that, that's definitely qualitative or categorical data. Okay? Good. So here are two different types of data displays that you could see with this type of data. Okay? Now, the first one is just called a bar chart, and this was an example of the Titanic. Did you guys read that example in your class, in your notes or your chapter 3? And I really like that example. We're going to use it not only today, but we'll use it later in the year for a different category, for a different example. But this talks about the number of people in each of the different categories. And if you read the chapter, you realize we talked about the different kinds of tickets you could buy. You could buy a crew ticket, a third-class ticket, second-class ticket, and first-class ticket. And it talked about what's there. Now, what's missing? A title, right? Anytime you need to have a title, right? And we probably need to also add something else. What is the frequency of what I'm counting? What would that be? The death, how many people died? Yeah. So that might be part of the title, and that would be okay, or you can label your axis that way. But you definitely need to create a title. So we could say like number of deaths on the Titanic. Okay, good enough? All right. Now, a relative frequency bar chart, what is the difference between the two? One's a percentage versus a count. That's really it. Okay? If you notice, the heights of the bars are still the same. Okay? The shape, we really don't talk about shape when we talk about qualitative data, by the way, okay? But I'm just talking about the heights of the bars are still the same. The categories, first, second, third, and the crew members are still the same. It's just that your axis is a little bit different, that's all, okay? The percentages. So which one do you think is easier to look at if I said, or I asked the question, maybe neither, maybe they're both the same. If I ask the question, which kind of ticket had the most deaths? Which one would be easier for you to use? Well, it doesn't really matter. Just looking at the height of the bar, right? So, well, they are still a member that's on the boat, right? So you're on the boat. So you're still a class of person. You still count, right? Okay. A second type of data display, bar chart's one of them. Oh, I forgot to go back to bar chart real quick. Sorry. What's the difference between a histogram and a bar chart? Because they are different. Okay, whoa, don't yell. Raise your hand. Tanner, give me one. Okay, that's one big one. The bars of the histograms touch. Okay, they have to touch. Give me another difference. Which is why they touch. Yeah, continuous versus discrete. It's not actually discrete because it's counted data, so it's a little bit different. But yes, continuous because it's measurable. All measurable things are continuous, meaning that the bars have to touch each other. There can't be gaps. Yes?
Speaking of the gaps, technically, couldn't there be gaps that say outliers?
Yes, and there will be gaps if there are groups that are separate from other groups. But what I mean by the bars have to touch each other, and that's what Devin was saying, is that this data is measurable and continuous on a scale. Yes? Yeah, histograms definitely describe shape. We can talk about shape with a histogram. We cannot do that here. The really big thing that I wanted you to pick up on that doesn't seem that anybody did is that the horizontal axis is totally different. In a histogram, what's the horizontal axis going to have on it? Numbers. And what does it have here? The categories. Okay? So that's really the big difference. Okay? Good. All right. Pie chart is something else that we will look at when we talk about categorical data or counts. And this is something that we don't use a whole lot because, well, I don't know. AP doesn't want us to use it a whole lot. So we'll talk about it a little bit, but then we probably won't talk about it again for a while. Okay? Now, if you look at these are two different views. You can get all fancy if you have it, your any kind of like an Excel or anything that will create a pie graph for you. I'm not sure which one is better, and they're just talking about the area of the wedge corresponds to the percent of the circle. Okay? So looking at this, does it also correspond to the bar chart? Does the crew have the largest percent of deaths? Right? The largest wedge of the circle would be crew, just like it was the tallest bar when we talked about a bar chart, right? Okay. Now, if I ever asked you to create a pie chart, okay, sometimes we call them circle graphs, but I don't really, some person out there. Do you know how we would actually construct it? It has to do with, hang on a second, it has to do with the amount of degrees that are in a circle. So think for a second about how many degrees are there, because I know I have some former geometry students of mine in this class. So you better know the answer to this question, Monica. Boy, you have like a deep voice, and you threw all the way over there. Ventriloquist. Okay. Shh. Let's ask Monica again. Monica. Oh, you did. I'm sorry. You did all the way over there. Do you have a question? Shh.
What if, say like the number of first class, tickets over, like the number total of people that were in first class, what the number was?
So we're not asking, so that's why the title is so important. I'm not asking you the number that died within each category. I'm asking it as a whole. Okay? That's a good point. Okay? This is just the number of deaths. I don't know how many survived. That's a different set of data. Do you understand what his question is? I think it's a pretty good question. That's why the title is so important, because that's what's clarifying the problem. Okay? He's asking, go back and look at the pie chart. He's saying, well, what if all the first class ticket people survived and all 325, or I guess died because it's deaths, right? So all 325 died. Shouldn't its wedge be bigger because it's a bigger percentage of those people? Well, that's not the data I'm displaying. Okay, I'm just displaying who died. I don't know who lived, right? That would be a conditional, okay? And so that's something we'll have to talk about when we get to that point. Okay, good. All right, let's look at this one. Here is a find a mistake question. Okay, Charles has a good point. Why is 50%, if that's the percentage that engage in some dangerous behaviors, and using alcohol, I would think, would be a dangerous behavior, especially at the high school level, not something I condone. And that wedge should be exactly half, right? Okay, Jordan. Perfect. Okay, that's one big thing. Those percentages, if they're going to create a whole wedge, a whole pie chart, those percentages should all add up to 100%, and they don't. Okay, awesome. Anything else, Temerson?
There's not a little spot for people who don't.
Right, which is why there's a wedge missing. Although I think that's kind of what you're talking about. But this goes back to the title. The title is, this is all students who do engage in dangerous behaviors. Based on everyone who does engage in dangerous behaviors, this is the breakdown of what I have. Okay? You understand that? That's why the title is so important. Yes, sir. Shh.
Well, you don't know the margin between alcohol use and...
What's the difference between those two things? Sure. Tanner, is that what you're going to ask me? Or say? The big two, the real big two when we're talking about it is the wedge of 50% better be half. So the size of the pie chart wedge should correspond to the correct percentage, and they should add up to 100. Okay? Big things. You'll see those in your homework tonight. Question?
I was going to say, shouldn't there be all three?
Could be. There sure could be. And how would you count that? Can I be in more than one category? Maybe I'm real dangerous. Maybe I'm an idiot. You know, who knows? Right, I think that's what they were saying, is what's the difference between the two.
Hi, Devin.
All right. Okay, so here's the third type of categorical data display that we could see. So far we've seen bar chart, pie chart or circle graph, and this last one's called a contingency table, or it's sometimes called a two-way table. Okay? And honestly, I call them both. I go back and forth, so I apologize to make you know more than one term, but they really are both accepted. Okay? So a contingency table, and this is, I think, one of the tables you had to look at when you read was about the survival rate on the Titanic, right? And so this is something that you were able to see. We have totals, row or column, are referred to as the marginal distribution. Okay? You need to know that word, so you need to write that word down. What is a marginal distribution? So if you want to copy this table down, this contingency table down, I think we should go ahead and put together what the marginal distribution actually is. Okay? So let me pause the recording for a second, let you guys copy it down, and then let's actually put those numbers together. Okay? Marginal distribution means I'm going to be using the numbers in the margins. That's really the easiest way for me to explain it. There are two different categories or two different variables that are being described here. Let's talk about what those two variables are. Give me one of them. Sammy, did you have your hand up? No? Okay. Give me one of the variables. In any contingency table or two-way table, there are two variables. Somebody besides Devin. I know Devin knows. Charles.
Whether the people survived.
Good. Whether they lived or died. Okay, so we have, how can we say that as a variable? Lived or died. Survival roots. They're all dead now, I get it, but okay. We'll say survival. So whether or not they survived or not is actually one of the variables that's being shown. What's the other one? Gender, okay? Whether they are male or female. So we have two different variables, survival and gender. And that's how we organize the data. One of the variables goes across the top, the other one goes across the side. And you just put the numbers or the counts in their respective boxes. So we know that 367 males, okay, that being the gender that we're talking about, survived the Titanic, okay? Now, when I'm talking about a marginal distribution, I have to know whether or not you mean, do I want a marginal distribution on gender, or do I want a marginal distribution on the survival? It's one or the other, okay? So I'm going to say I want us to talk about the marginal distribution for gender, okay? So let's do that. What would that look like? So the marginal distribution for gender is really just a series of ratios, okay? How many different ratios am I going to talk about with gender? Two. Only two. We're looking at just the margins. I have males and I have females. Would you agree with that? Okay. So we're going to only use the margins. So I'm only going to use those numbers in my marginal distribution for gender. If I ask you for the marginal distribution on survival, wouldn't I use the last column? Those are the numbers I would use. But since I'm talking about gender, I'm going to be here. So I'm going to say, okay, the number of males on the Titanic, and this is on the Titanic. Now I care about who's alive and who's dead, right? Even though I know they're all dead now, but that's not the point. At the time, that's what I meant. It's going to be 1,731 divided by what I like to call the total. This guy right here, okay, 2201. And you should probably give me both the ratio or the fraction and the percentage. So someone divide those out and tell me what you get. What is the percentage of people, of males on the Titanic? 78.6%. Okay. Let's do the same thing with the females. Have you ever seen this notation, by the way? Yeah. I use it all the time, so just sorry if you haven't, but this is our female notation, okay? Males and females, and we're going to say 470 of the passengers, whether they were crew or first class, second class, third class, 470 people were female. And why do you think there were so more fewer? Wow.
A lot of businessmen were going over.
Okay, what else, Sam? Almost all the crew is going to be, I shouldn't say all, because I would imagine there would be some like dressing ladies or something back in those days, but most of the crew would be male. I would agree with that. Okay, so and what percentage should this be? They should add up to 100%, right? Do they? Okay, according to the subtraction, yes. But when you divide them, is it as well? Because when you add them together, they add up to 100. Oh, it's 21. Andrea, hi, Smarty. Throw me a Smarty. You are Smarty. Sweet. All right. That is the marginal distribution. I think one of the questions on iColor that you guys had to do asked you to find a marginal distribution, didn't it? That's all I'm looking for. Find the variable they're talking about and find the percentages. It's that easy. Okay? Now, freaking me out. Okay. That was kind of weird. Now, we talked about marginal distributions. We know what those are. The last time we know what marginal distributions are, sorry. I want to talk about conditional distributions. So, hang on. They're a little bit different. Let's go back to that. Let's go back to this guy. Okay? So, marginal distribution. The other kind was conditional distributions. Did you read about those in Chapter 3? And when I say the word conditional distribution, how is that different? Somebody, I know Devin. No, somebody besides Devin. Okay? What is the difference? The marginal uses the margins. What did the conditional distributions use? Temerson?
The ones like dead and the ones that are alive. Like the totals for dead.
We actually don't use we use the total sort of. You're actually going to use the numbers on the inside of the tables. Okay? So you're going to actually use the inside stuff. Okay? So if, for example, I say, let's talk about the conditional distribution for those who lived on the Titanic. Okay? So that's going to be a little bit different. So let me go ahead and write that down here. Oh, calcified. Know what I'm doing. There we go. So let's talk about the conditional distribution. For the alive people. Okay? So the conditional distribution for alive people. So in this case, I'm not going to worry about the margins so much. I'm talking about the alive people. Right? So the conditional distribution for the alive people means that you're going to, not the total totals. You're going to divide by that total rather than divide by the total total. That's why I call it the total total, because it's this number, it's the total total. It's the total of the totals. Let's keep going. Okay? What numbers am I going to be using? I'm still going to be talking about those who are alive. We have males that are alive, and we have females that are alive. Do you agree?
Yes.
Now, what numbers go in my conditional distribution? 367 divided by 711. Okay? So, what percentage is that? 51.6? Thank you, Erwin. 51.6%. So, of those people that lived, 51 or almost 52% of them were male. Okay. Now, how about female? That would be 344 divided by 711, which was 48.4%. Well, hang on a minute. Hold the phone. Okay? Something's strange in my neighborhood. Okay? Why? Those percentages are close. But then if you look at the marginal distribution for gender and the males and females, they're really far apart. Because you told me, Sam said, most of the crew is male. And he's right. Okay. Okay. So here's a question I have for you. Okay? Shh. You ready? Ready for the big idea of the day? Are my two variables independent? But don't just scream out an answer. Okay? Hold it in yourself for a minute. Is survival on the Titanic independent of whether or not you were male or female? So again, we decided, I said don't yell it out. Think first. Gender versus survival. Those are my two variables. We decided that at the very beginning, right? Trying to decide if they're independent or not. There is more than one way to answer this question, and we will do it again when we get to our probability unit. So we'll talk about conditional probabilities and that kind of thing. But from just a categorical data perspective, we can actually compare the marginal distributions to the conditional distributions and answer the question. Because there was a higher percentage of just males on the boat, but half of those males died, over half, and women, there weren't as many, but half of them died too, right? Well, you either lived or died, so they're complements of each other, right? So it's not a big deal. Shh, guys. Shh. Okay. So because these numbers are different from each other, okay? And what am I comparing? Males to males, females to females. Okay, I am comparing 78.6 to 51.6. I am comparing 21.4 to 48.4. Because these are so different, we can say they're not independent. That's important, okay? So I'm going to say that again. We are comparing these guys. Because they're different, they're not, we call them dependent. Okay? So therefore, gender and survival on the Titanic are what we call dependent variables. Now, this should make sense, because if you think back to that time frame in American history, which was 1912, 13, when did Titanic sink? 12? That's Downton Abbey, only reason why I know. Okay. So 1912. We should know, thinking back to that time frame and that age, if you guys do watch Downton Abbey, like I'm an addict, love it. We know about that time in history. Why does it make sense that gender and survival are dependent variables? Someone who hasn't answered a question yet today. Lena's always quiet. Why does that make sense? Why do you think that's true? Yeah. Okay, more men were working, true. That's it. The chivalrousness of the men, right? The men, if you ever watched the movie or read the book or did anything about the Titanic, who were the first people on the boats? Women and children, right? So you're exactly right. So this does make sense that they are dependent. You had a higher likelihood of survival if you were a woman or a child, right?
So when you say
Excuse me.
variables, do you mean like they're connected to
They're
each other?
connected to each other. It means that gender and survival was dependent on each other because you were more likely to survive if you were a woman. Okay? Now, can we think of two variables that might be independent, that have nothing to do with one another? Two variables. You don't have to, it doesn't have to be Titanic specific. It can be anything else. Any two variables. Yes, ma'am. Shh. Give a question first. Go ahead. Let's say it was like 70 and 69, and if they're like 1 to 2 percentage points off, then I would say they're close enough. Now, there's an argument there. You have to say, yes, they're close enough, and we can go for it from there. When we get to probability, there's an exact way to do it. You have to talk loud, babe. Yes, if they are close, the closer they are together, the more independent they are. Okay, that's a good question. Hunter? Grades is measurable. I guess unless you said something like A's, B's, C's, D's, E's, then you're at categories. Maybe, yeah, possibly, because does it necessarily mean that women are smarter or girls? Who knows? Maybe I could go for that, but because grades are measurable, that's kind of hard. Yes?
With gender and eye color?
Gender and eye color is a great one. Okay? Because those are definitely two categorical variables. Are there more blue-eyed males? Probably not. Well, according to that. Well, hang on. Shh. Can we address that actually, Amanda? Okay, shh. Guys, all the little conversations. We're going to have new assigned seats on Wednesday. I can't wait. Seriously, your class is too big and you all know each other too well. I'm putting you next to someone you don't know. All right. Let's go back to Amanda's point. According to the homework, there were more blue-eyed males. Well, that's according to that sample. Okay? And when we talk about sampling variability, big key word, you need to know what that means. Samples vary from one to another. And so this particular sample had more blue-eyed males in them. Well, what if I took another sample over here and it had different data? That's okay, because samples are going to vary from time to time.
And
Okay?
genetically, gender, and color are not related.
Right, that's what we were saying. They're independent variables. Good example. All right. I'm going to skip a couple slides here. Okay, I'd like to go ahead and look at the just checking now. Okay, so I'm going to turn the light on. I'd like to go back to the just checking from the homework, and let's actually make sure we can answer them properly, because so many people had questions on it. Okay, there we go. So, and any time that, and by the way, this particular, I didn't fill in the totals. I believe that there is totals listed on page 28, right? Anytime there are not totals in your two-way table, like I believe that'll happen on your homework tonight, you need to make sure you include them. So that's why I left them blank here. But you really should go ahead and just add those in, if you would, please. And it's 64, right? And what do I have? 32 and 34. Okay. So we had the exact same amount of males and females in our survey, right? Okay. So let's look at our contingency table and make sure we can answer some of these questions. So what percent of females are brown-eyed? So whenever I ask this kind of question, I want you to not only tell me the percent, but show me how you got it. What divided by what? So I'm looking for like the work involved, if that makes sense. So I'm looking at what percent of females. That tells me what I divide by. So I'm going to be dividing by 32. Okay? And what percent of females are brown-eyed? How many of them are brown? Of the females is 16, right? And so what percent is that? 50%. Okay? So that should be your answer to the first one. Let's double check our answers in the back. Remember where those are now. And we're right. Yay. All right. What percent of brown-eyed students, again, of brown-eyed students tells me what I'm going to divide by. What's the total of brown-eyed students? So I'm going to be dividing by 36 here. Are females. So again, 16 out of 36 this time. And what would that be? Good. To the nearest tenth is usually a good idea, never to a whole percent. Okay? Now, go back and look at those questions. What percent of females are brown-eyed? What percent of brown-eyed students are females? They're two different questions. Okay? Notice we got two different answers. So it's important to know how to set up your problem. All right, number 3, what percent of students are brown-eyed females? So of students means I'm dividing by 64. And then we're looking at brown-eyed females, which in this case, we have brown-eyed females. So we're looking at 16, in this case, divided by 64. And so when we do that division, we get 25%. And since it's asking for a percent, I am looking for a percent in this case. Now, I think Temerson had a great point. He asked me a good question. He said, what do they mean, Ms. Macker, by number 4? Do they mean a marginal distribution? Do they mean a conditional distribution? Since they're talking about the distribution of eye color, they're really, I believe, talking about a marginal distribution of all the different types of colors of eyes. Now, if it were me on a quiz or a test, I would probably be as specific as possible and say marginal, but I think that's kind of a good question. So, marginal distribution of eye color. I need to say what the eye colors are. So you're going to say blue is going to have this percent, brown is going to have this percent, and what's the other one? Other. How about if I just say other? Us green-eyed people, we always get the shaft. Okay? So blue would be 10 out of 64. Good. And you could write the corresponding percentage, and I believe it's 15.6%. Brown would be 36 divided by 64, and other would be 18 out of 64. And again, you should probably write the percentages down. Okay? Are we okay with where those numbers came from? You sure? Okay. Now, Let's look at number 5. Number 5 is asking for the conditional distribution of eye color for the males. So, let me I don't have enough room to write it here. Do you mind if I write it underneath? Okay. So, I need to be careful. We're looking at the conditional distribution of eye colors for the males. So, we need to figure out what set of numbers we're talking about. Okay? So, since we're only looking at males, these are the numbers I'm talking about. Okay? And I'm going to say just for males, we also have blue, green, blue, brown, and other. Well, blue and other. So, what am I dividing by? 6 divided by 32. Very good. And again, you can write it as a percent. And then we'd have 20 out of 32. And we would have 6 out of 32. And again, just knowing what to divide by is half the problem here and half the battle. Emerson, where are your glasses?
I lost them.
We need to get you some more. Okay? Any question about 4 and 5? Here's a question I have for you. If we know what the percentages are, and we can find them pretty quickly, are gender and eye color independent? Number 7. Let's jump to that question. How could I answer it using what I just did? Because you can. What I mean is this. Let's go ahead and write the percentage. What's 10 divided by 64? I'll just write the numbers. 15.6. All right. And brown was 56.3. Other was 28.1. Now we're going to look just for males. I have 18.8%, 62.5%, and 18.8. So again, just by comparing the marginal distribution to the conditional distribution, again, we're comparing blue to blue. We're comparing brown to brown. We're comparing green other and hazel to green other and hazel. Think about it just for a second. Are you going to answer my question, or do you have a question?
I have a question.
Okay.
One percentage is wrong, so it adds up to over 100.
Okay. I'm just going by what this is just, thank you for checking that for me. We had to round these to get to that point, so since we rounded, it might be 1 or 2, it might be like a little bit over, a little bit under. Okay? Let's compare and ask the question one more time. What do you think? Aditya, what do you think? Are they independent or are they dependent? Are eye color and gender independent or dependent according to our data? Are the percentages close enough? Okay? Anybody have a differing opinion, or you all agree they're close enough?
No.
Well, I guess what my question to you would be, what is close enough? I think like more than 10% is kind of a lot. If you look at the other category, aren't those off by 10? That's kind of a lot. Okay? So according to this data, this particular sample, right, it appears as though gender and eye color are dependent. Or at least all we can say is we don't have enough information to say that they're independent. Okay? I like that way better too, actually, because they're really not dependent variables. Yes?
I know, like, there are stories blue eyes, like, with the
For males, exactly.
it looks like
Yeah, it wasn't within the last 100 years, right?
it was in the question here, but before, like, I found a lot of people had brown eyes or brown hair.
Yeah, I don't really know the answer to that. That's a good question. I'll look into it. I know it was a genetic mutation for males specifically, not like 100 to 200 years ago, but that's all I know. Yes, shh, folks.
Number 6.
Yes, let's go back to we skipped number 6, didn't I?
Oh, we didn't do number 6?
I hadn't. All right, so let's go ahead and answer question 6 to make sure we fully understand. Okay, because I kind of skipped it because really the only thing you needed to answer for number 7 was 4 and 5. Well, let's come back to 6. So number 6 is compare the percent who are female among the blue-eyed students. So let's write that percentage down. So who are female among the blue-eyed students? What am I going to divide by? The blue-eyed students. So 10, right? So the females among the... Guys, stop yelling at me, please. Thank you. The female among the blue-eyed students is 4 out of 10, or 40%.
No.
Yes.
Asking for all students.
Okay. Please let me finish. Okay. It's asking who are female among the blue-eyed students. Here are the blue-eyed students. Those are the females among the blue-eyed students. Okay. To the percent of all students who are female. So now we have to look at all students who are female, which is going to be 32 out of 64, which is 50%. Okay? Emerson, is that okay?
Yeah.
You sure?
Yeah.
Okay. That's all you have to do for that particular problem. All right. So many of us miss these questions. These were the just checking. And again, if I ever assign the just checking again, what am I looking for? Work. Okay, good. Let me go ahead and assign you your problems from chapter 3. Here it is. It says 1 or 2 or 3 or 4. Pick one of them. Which one looks happy to you? 4? You like 4. Do 4. Okay, Stephanie's going to do 2. Goodbye. Okay? Pick one of those. I don't care which one. No, pick one of them. 1, 2, 3, or 4. And then you have these 4 you must complete. Okay? Huh? That's page 36 to 39. Okay.